Hello everyone, welcome to my latest video on how to calculate pi like Archimedes did. And well, nowadays there are many better ways to calculate pi than I'm about to show you. That's how we've calculated trillions and trillions of digits. But most importantly over here, I want to show what was the leading method to calculate pi for centuries. And to show this, I want to first make sure that you know some basic geometry and all, like the Pythagorean theorem. That's pretty much all. And well, if you want to go even further, you need to know trigonometry. So it's actually pretty easy to prove that pi is between 3 and 4, but to go further, it's kind of difficult. But for today at least, I'm going to try and prove something kind of simpler, and I'm going to prove that pi is between, as you can see over here, is going to be between 2 root 2 or 2.8, and it's going to be between 2.8 and 4. So how am I going to prove such a thing? Like, just how? Well, what's the easiest way to calculate pi without really that much math? Well, we know that the circumference of a circle is going to be pi times its diameter. And so to find pi, we can just divide both sides by diameter and we get c over d. So you could just go to your house or so and just take any whole circle, as long as it's a circle. It's almost kind of bad. You could just take a circle and try and attach a string around it and straighten out the string and calculate its size so you can find the circumference. Once you have the circumference, you can divide it by the diameter of the circle to get pi. So it's just the circumference divided by the diameter. But this, of course, has measurement errors. So, well, it's not really that accurate. Of course, you could still get kind of a close value, but it's not so accurate. So what is a better way to find this? Well, let's see. What we're going to do is the way Archimedes did it. And we're going to do this by, well, first show an example. Say we have a circle, once again, with radius 1. We know its circumference is going to be 2 pi. So what I'm going to do, I'm going to put 2 pi right here. And I'm going to try and find a value that is more than 2 pi and a value less than 2 pi. So we can bound 2 pi between two values. Well, let's see. I'm going to draw a square such that it's inside the circle. And so it's this length right here is going to be 1. So its full diagonal is going to be 2. But now I'm also going to draw another square, this time outside the circle, in such a way that its side length is going to be 2, because this is going to be 1, and so this is also going to be 1. So its side length is going to be 2. Well, here's what we know. The perimeter of the outside circle, which we know its side length is 2, as I just showed, is since its perimeter is going to be 8, we can say 2 pi. Oh, well, 2 pi is going to be less than 8. And the way I can say this is because I know 2 pi is the circumference of this circle, and since the square clearly has more perimeter than the circle does, we can say, okay, 8 is going to be more than 2 pi, since it's more. And now we can also find the perimeter of the one inside and say, oh, well, it's less. It has less perimeter. So if I want to find out what the area is, the perimeter is, well, firstly, I know this radius right here is going to be 1, and so its whole diagonal is going to be 2. Let's go down, redraw the square. The diagonal 2, and we have two sides x, and let's just try and find the sides. so we can multiply it by 4 and then find the perimeter. So we know that via the Pythagorean theorem that x squared plus x squared is equal to 2 squares, because a squared plus b squared is c squared. This relationship right here. And so we can know that 2x squared is equal to 4. Dividing both sides by 2, we get x squared is equal to 2. X is equal to square root of 2. And via this way, I can clearly say, oh, well, x equals square root of 2. Okay, so this side is going to be root 2. And so we have 4 of them. So we can say 4 root 2. That's the perimeter of this inside square, which is going to be less than 2 pi, because 2 pi is the circumference of the circle here. So now what can we do? We are supposed to find pi. So let's divide the entire inequality by 2. And so we get 2 root 2 is less than pi is less than 4. So what have we found once again? 2 root 2 and 4. Well, we know that 2 root 2 over here is about 2.82 or something. So we know it's between 2.82 and 4. But, well, we can't really find an exact value just yet. We just found that it's bounded between these two values. A good way to try and find a more exact value is probably average the two values and see, oh, we get about 3.41. But of course, we know for sure that pi is going to be between 2 root 2 and 4. That's all we know for sure. So, but now I want to show a more general approach to this, and you'll need to know trigonometry if you need to see if you want to see exactly how they found larger and larger values, or larger and larger side lengths for these polygons. Because right now we use a square. Imagine we used something like this, like something really close to what the circle is. Like, say we had a circle, and instead of using a square like we did, we could use like a polygon that's like this. And so if we use something like that, we approximate it so much better than what we did with the square, because you can clearly see the square is so much more off. And so I'll show you exactly how to do that. All right, so say we have an arbitrary circle, all right, and we are given its two, we're given a polygon, all right, it's an n-sided polygon. This means that one side of it, what inscribed inside the circle, would look like this. Let's work with the inside first and the outside next. So when it's inside, it will look like this. Where this angle is going to be 360, or I'll work in radians. Just well, I mean, if you want, I could work in radians or degrees. But honestly, I think degrees will be better for the general case. So I'm going to just work in degrees right now. So 360 over n degrees, because, well, there's going to be n sides. That's 1, 2, 3, 4. How many of us sides we're going to have? We're trying to work for the general case, remember? And so we know this is going to be r, or the radius in this case. And so since we're going to have the radius to be 1 always, I'm going to just show, alright, radius is going to be 1. And so what are we going to do? Well, now that we have the said triangle right here, 1, 1, and 360 over n, well, here's what we can do. We're going to use law of cosines to try and find this side right over here. And once we found this side, which is this side over here, by the way, we can use that to find the perimeter, just multiplied by n. So we're going to use the law of cosines here. And just a refresher, law of cosines is that a squared plus b squared minus 2ab cosine of theta is equal to c squared. And this is where A is this side, B is this side, and theta is this angle right here. And so let's try and find it. So 1 squared, which is 1 plus 1, so 2 minus 2 times 1 times 1 times the cosine of 360 over n, 360 degrees over n, is equal to c squared. And I want to emphasize here, exactly how are we going to take the square root on both sides, since we're subtracting these two things. And so the best way we can do this right here is by taking a 2 out, like right just like that, and doing 1 minus cosine of 360 degrees over n. But still though, how are we going to take the square root? And this is important. We're going to use an incredibly special trig identity. And that trig identity is saying 1 minus the cosine of theta is equal to sine squared of theta over 2. And this is quite a useful trig identity here. It's useful in this particular case, to be specific. So we can say, oh well, 1 minus cosine 360 over n, we can rewrite that as 2 times, I'm going to remove the brackets here, sine squared, which by the way is just the sine, we put brackets over the whole thing and square it, of 360 over n over 2. And so we can simplify this inside part to be 180 over n instead, because 360 over 2n, and then the 2 cancels out with like the 360 becomes 180. So we can get 2 times sine squared of 180 degrees over n is going to be equal to c squared. And if you're still confused on how this simplifies to this, just try and do it yourself, and you might see. Now we can take the square root on both sides. And since these two things are being multiplied, I can take the square root of 2 out, like this, and get sine of 180 degrees over n. And the reason why the sign didn't change is because the sign over here didn't change, because initially it was sine squared. Now it's just sine. And this is equal to c. So sine 180 over n times root 2. So that's what we know. And so how is this going to help? Well, remember what I said. This is going to be this side right here, this one side. And we multiply that side by the amount of sides that exist to get the perimeter. And so we can conclude 2 um sorry 2 pi is going to be more than the perimeter of the one inside, right? Because the circumference is going to be more than the perimeter of the one inside. So 2 pi is going to be more than n times sine of 180 over n times root 2. So n times sine of 180 over n times root 2. So from all this work, we can clearly see how this happened. And so we have this, and we're also going to try and find the other side of the inequality as well. So what's more than 2 pi? Well, remember what we did with the square. We try and find the outside. So you know what? Let's do that. Let's find the outside. And so the outside now, once I manage to draw a good circle, the outside is going to be, since it's going to be more than 2 pi, we can put it on the other side of the inequality. And so we have this, 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 and so we know once again we have an n-sided polygon. We're going to keep this n to be the exact same. And since each one of these lines are going to be tangent, well, what we can say here is, well, to find the area of the figure, well, what we can do here, hold on, there's a 2 here. I forgot about that one. And so to find the initial area of this figure, what we can do is draw this little line right there and see that this is, oh, well, this is 360 over 2n. And how do I know this is 2n? Well, remember, this is going to be 360 over n, since that's one side, like we did before. So it's 360 over 2n. But remember, 360 over 2n is just 180 over n. And so now that we have that cleared, let's go on and attempt to find the exact value of pi. And, well, in this case, we're trying to find this side right there, knowing that this is going to be equal to 1. And we know this, and we know that's a right angle. So, let's draw that out. Here's the right angle. Here's the 180 over n, degrees over n. And, well, the side, yeah, this is 1. And the side we're trying to find right here is going to be this x. So it's a right triangle, so we can just do a sine ratio. I mean, a tangent ratio here. Because we can say, oh, well, the tangent of 180 degrees over n, because SOHCAHTOA is going to be opposite x over 1. Opposite over adjacent. So x over 1, such as x. So we know that side over there is going to be tangent of 180 degrees over n. So this side, but to find this whole side, we have 2 times tangent of 180 over n. So this whole side is going to be 2 times tangent of 180 over n, 180 degrees over n, because this is tangent of 180 over n. And so we're trying to find all the sides together. So together the perimeter, all of it, is going to be n times 2 times tangent of 180 over n. So I'm just going to erase this now. Just leave some space. So since we now have 2 times n times tangent of 180 over n. I forgot the degree symbol. The degree symbol is kind of important. If you don't put the degree symbol, most people just assume you're talking in radians. And so now, what we can do is, well, we did all this to find 2 pi. Let's divide all the sides by 2 to get n sine 180 degrees over n is less than pi is less than n tangent of 180 degrees over n. And so what are we going to do? And this is important. We calculated pi. I mean, we found a good way to approximate pi. As we increase n, which remember that it means increasing the amount of sides in the polygon, we can get closer and closer and closer to the actual value. But how much does that actually help us? Well, if we think closely, the amount that, well, in this particular case, it might not help us as much as you might expect. Because, I mean, you might just be thinking, oh, just plug in n, larger and larger values of n, 2,000, 10,000, or something. But if you think about it, well, nowadays we have better algorithms, but this is how they used to do it back then. They didn't have a calculator. So how are they going to calculate sine of 180 over 100 or something? So sine of 18 degrees. How are they going to calculate that? And this is the important part. How did they calculate sine values? And well, they actually had very ancient tricks to calculating further and further sine values like they did over here. And if you want to see that, um, I suggest you might subscribe or so because I'll probably cover that in another video as we're running out of time here. But how they used to calculate old sine values is actually really cool. Like sine of say 15 degrees. We can actually prove that sine of 15 degrees is actually the square root of 6 minus the square root of 2, the whole thing over 2. Yeah, we can actually, there's actually a proof for that. Sine of 15 degrees is equal to the, uh, the square root of 6 minus the square root of 2 over 2. Now let's actually see that. Sine of 15 degrees. Okay, it has to be in degrees. Change that to degrees. Square root of 6 minus the square root of 2, whole thing over 2. Okay, I was wrong. It's actually the whole thing over 4. But you can see uh, that they are nearly identical. But what if they aren't identical? Well, there are actually proofs for this. And it's actually really cool to be able to see sine values and, well, to be written in such a format. Because, I mean, it's commonly thought that some of these sine values are transcendental, but they really aren't. And these identities, they come from these special formulas called trig identities. And once again, I'll show that off in another video. And so, as you can see here, I plugged in the two little things that we found over here. And so, what I'm going to show you here, what? So I have n sine 180 over n. This is supposed to be less than pi. And n tan theta 180 over n. This is supposed to be more than pi. So pi, or the value of pi, is going to be between them. And you can see it is between them. But we're choosing a really small value for n3. This means we're doing a triangle. That's not even it's not even a square. That's literally a triangle. When we increase it over to a square, we can see our upper value is 4, lower value is 2.82 or so, just like we found. And as I keep increasing n to larger and larger values, you can see why this method becomes quite useful. Now we can see pi is between 3.141 and 3.142 or so, and we can clearly see the how close it is to the values. And as you increase it to incredibly large numbers, like 100,000, which by the way is incredibly difficult, so nearly nobody is going to do 100,000 or so. Most people, they work in powers of 2. So they try and do 2 squared, 2 to the third, 2 to the fourth. And if you want to know, there's actually a reason for that. The largest polygon they have found uh, before Isaac Newton found a better way to calculate pi, is a 2 to the 60th polygon. And you can see the Desmos, which is the calculator I'm using, can't even tell the difference here. They all look the same. And by the way, this calculates for about 50 or so digits of accuracy for pi. So this is way better than the normal method. Only problem is the person who calculated this spent like 50 plus years of his life doing it. So yeah, it was an inefficient method, but it was their best method at the time because the measuring one, there's a limit of accuracy you can get. But with this, you just continuously apply this algorithm, which I might show in later video. But at the same time, it's basically just plugging n here. The hardest part here back then is the fact that they didn't have calculators. So these sine and cosine values, they had to find it themselves. Well, the sine and tangent values in this case. And because they had to find it themselves, it caused huge troubles. As once again I had shown, they had to find out, oh, well, I mean, sine of 30 degrees is equal to, is 1 over 2. But then they also had to find stuff like sine of 15 degrees, which, as I had shown, is square root of 6 over minus square root of 2 over 4. And they had to keep finding these sine values. And so they had to do these really complex derivations using stuff like half manual formulas and stuff. And so it was really difficult to do it back then. But this is a very well working method to find pi. Just plug in really, really large values of n and just try and find the best result you can.